So in this lesson we're going to introduce energy. We spoke in previous lessons about the quantities work and power, and in this class we're going to look at introducing energy. So first of all, make sure you know your definitions. So this first page I'll be flipping from, pause it, make sure you understand basic things. But energy ultimately is defined as being the capacity to do work. If something is capable of doing work, then it has energy. Remember, work means some kind of force is being applied over some kind of distance. So if it's capable of doing work, applying some kind of force over some kind of distance, well then it has energy. Various different types of energy, I'll read them out, but they're listed there: thermal, radiant, chemical, nuclear, electrical, motion, sound, elastic, gravitational energy. But it's categorized ultimately into two broad categories, and they are kinetic and potential. So that's all we're really going to be talking about on our course: our kinetic energy and potential energy. If I add the kinetic and potential energy of an object, that's called the mechanical energy of the object. It's the sum of the kinetic and potential energy. And so in other words, it's the energy in an object due to its motion or due to its position or both. And we have a couple of little equations here, I suppose definitions. The kinetic energy of a body, we usually use this notation: E sub k equals a half times m times v squared. V in this case means speed as opposed to velocity. So V here means speed. So for example, if something was moving with a velocity of 3I hat plus 4J hat meters per second, well, its speed in this case would be 5. So really we mean the speed of the object. Okay, so speed in that case would be 5. M represents the mass as usual. Potential energy is defined as m times g times h, where m represents mass, g is the acceleration due to gravity, and h is its height. It's based on its position. Okay, we're going to take h as height. Principle of conservation of energy. This is in your formula and tables booklets. It says the change in a conservative system, of course, and we'll talk about more about that. In a conservative system, the change in potential energy plus the change in kinetic energy is always equal to 0. In other words, the change in mechanical energy is 0. So the sum of its potential energy and its kinetic energy doesn't change in a conservative system. An example of this kind of system is gravity, where the only force acting on the object is gravity. An example of a non-conservative system is maybe something where friction is coming into play, so dragging a sled across the ground. That's not a conservative system, but throwing an apple straight up in the air, is a conservative system. Okay? So those are important. It's important that you get your head around those kind of basic concepts. Remember these two equations. We're going to be coming back to those over and over again. Remember the principle of conservation of energy. We're going to be coming back to that often. Okay? In a conservative system, conservative system is a system where the energy is conserved. So I just want to have a look at a couple of things. I want to start by just looking at kinetic energy. And kinetic energy we've defined as being half times m times v squared, where v is the speed. So if I take, I've put in some titles here. One thing you could do, before you do anything, I suppose, always a good thing when you see a formula is to change the subject of the formula. So I can, make m the subject of that formula by multiplying on both sides by 2. Be doubling the kinetic energy, and then dividing on both sides by v squared. So the mass will always be twice the kinetic energy divided by v squared. And every time you get a formula, this is just a good thing to do. I can make v squared the subject of the formula, V squared will be equal to multiplying on this second equation both sides by V squared, dividing on both sides by M. We get twice E sub k over M. So I can make different things the subject of the formula. To find V, then I just take a square root to figure it out. And V represents speed, so we're talking about something that's positive here. Kinetic energy is always a half times the mass times the square of the velocity. So if I want to find the kinetic energy, I'm given the mass of 20, given a velocity of 5. Well, a half of the mass would be 10. The square of the velocity would be 25. And so I'd be getting a half of 20, 10, times 25. I can write that out. A half times 20 times 5 squared. But I'm hoping you can see that's just 10 25s, which is 250. My units for energy, well, energy is the capacity to do work, so my units for energy are joules. The same as my units for work. To find the mass, again, I'm just going to change the subject of the equation. You can take your basic kinetic energy equation and plug your value for E in there on the left, plug your value for V in here on the right, and then solve. Or I might just use this second version of the equation, which says to find the mass, I double the kinetic energy and then divide by the square of the speed. So I'm going to double the kinetic energy and then divide by the square of the speed. So I can do that. That's going to be if I've already changed the subject of the formula. Okay, so doubling the kinetic energy here will be 196 and dividing by the square of the speed here. So doubling 98 and dividing by the square of the speed 49. So 96 divided by 49, what's that, 4 I think, yeah. 49 goes into 98 twice, so going to 196.4. My units in this case will be kilograms because we've got joules and meters per second. Okay, and the last example, again, there's my basic equation. I can absolutely substitute 12 in here for M. I can absolutely substitute 216 here for E and then solve it. In fact, that's what most people would probably do. I'm going to actually just use this version, which says the square of the speed is going to be double the kinetic energy. That's double 216 divided by the mass, which in this case is 12. And if I do that, I think I'm getting 36 meters per second. You might just double check all my arithmetic here. Okay, so that's kinetic energy. A little formula, practice changing the subject. Okay, same with potential energy. I can make the mass the subject of the formula. The mass is going to be the potential energy divided by G times H. Remember, G is just a constant. On the ordinary level course, we take it to be about 10. On the higher level course, we take it to be about 9.8. Okay, I can make H the subject of this formula by dividing on both sides of this by mg. It'll be the potential energy divided by mg, mass, multiplied by the acceleration due to gravity. So potential energy here is just going to be m times little g times h. So 20 times h, which is 5. 20 times 5 is 100. Times g, that's just going to be 100g. Okay, and my units are joules. So if I take g to be about 10, that'll be 1000 joules. If I take g to be about 9.8, that'll be 980 joules. To find the mass, we divide the potential energy by g times h. So here we're dividing the potential energy, 98, by g times h. G times 1 is just g, so we'd have 98 over g. And I'm going to use g to be 9.8 here because it'll work out quite nicely with that 98. That's going to be about 10. And mass is measured in kilograms here. And to find the height, it's just the potential energy. In this case, that's 6,997.2 joules divided by m times g. Well, that's 42g. Okay, so 42 times 9.8. If you're dealing with higher level, ordinary level, we take G to be about 10. So I'm going to grab a calculator here and divide 6,997.2 by 42G. I'm getting 17. Taking G to be 9.8, I'm getting 17. And my units in here are meters. Okay, so get used to working with these couple of equations. They are important. Okay, so practice those things. In our next class, we'll talk about the principle of conservation of energy. But that's good enough for now. Practice those things. Make sure you can fill in those tables. Get used to the definitions going forward. Make sure you know what energy is and the difference between kinetic and potential energy. How to define mechanical energy.